And those are pretty much all of the answers to the quiz. Congratulations for the people who actually attend class. Now we're going to learn a little bit. We're going to spend a lot of time understanding flux, how to calculate flux, given a current, and then the magic of Lenz's law, which allows us to find which direction induced current flows. And that's the capstone of this module. If we get there and I get lots of people actually successfully understanding that, I will be muy happy. Okay, let's do a little bit at a time though. Let's build up to this, build up the pieces. If you don't understand what flux is, you can't understand the higher pieces. So let's start with understanding flux. Let's calculate flux. Let's do examples of flux. Okay, so flux, phi. What is it again? How do you calculate it? Bah. Flux is BA, magnetic field times area. Suppose we take, the Earth's magnetic field and pass it through, a 1 meter square, let's do it different. Half a square meter loop of wire. I'm going to make a loop of wire that's half a meter, half a square meter of area. Should be, isn't it? Yes, it is. Thanks for checking. Okay, so again, the first question here for you to think about is, suppose I've got Earth's magnetic field, 52 microtesla. You can round it, 50 microtesla. And that's passing through a 0.5 square meter coil of wire, loop of wire. Find the flux. Google Form B. Again, Earth's magnetic field, 52 microtesla, area 0.5 square meters. Round it, 50. If I tell you that the magnetic field of the Earth is about 50 microtesla, and if I tell you that the cross-sectional area is half a square meter, how much flux do you got? Oh, that's right. We need to practice scientific notation. Oh, I don't want to do it today. Huh? Line? What's line? Lion? What you talking about, boo? The lion? Is there a lion in the room with us right now?
No, I was stating a me.
Oh. Oh.
I said the lion would not concern himself with scientific notation.
Okay. I do not know that one, as is probably bleedingly obvious. All right. The correct answer is 25 microtesla, which can be written in scientific notation as 2.5 10 to the minus 5 Tesla. I just remembered that's a skill we have to practice. We've got enough going on today. We're not going to do our mini unit on scientific today. I multiply B times A to get flux. By the way, hey, I can actually make a loop of about that area. Here, I've got a loop of wire. The flux in this right now is actually 0. You know why? So I'm holding it sideways to the field. Earth's magnetic field is pointing this way. None of that field is actually going through the loop. So it's not really just B times A. You've got to consider, is B going across the area or going through the area? I'm not going to give you any trigonometry things where you have to do sines and cosines here. Yeah, question. Did I say Tesla? I'm so sorry. The correct answer should be in Weavers or Tesla meter squared. 2.5 10 to the minus 5 Tesla meter squared. Thank you. Okay, so I'm going to assume throughout the entire rest of the lecture, by the way, that I have arranged things so that you don't have to care about the angles. I'm not going to give any tricksy things about the field is sliding along the area. I will only ever have piercing through the area. You may need to care about this. We'll talk about cases where you care next week. All right, so magnetic flux is B times A. Let's say, by the way, I hold this loop up for 10 seconds. After 10 seconds, what's the voltage in the wire? You've just calculated that flux equals, what did we just say? 2.5. 50 times 5 is not 6. Oh, it's 50. Okay, whatever. That's where it comes from. Whatever. 3-ish. Okay, I actually properly I only gave you 1 sig fig, so we should round to 3 times 10 to the minus 5 would be the correct answer. Whatever, here's 5. I'm going to ask you, after 10 seconds of holding this here, how much voltage is induced in the wire? What is this? See? I'm going to hold up a loop of wire perpendicular to Earth's magnetic field. This is about a half square meter. And I'm going to ask you after 10 seconds how much voltage is present in this wire because of Earth's magnetic field. Do this individually. Don't talk to your neighbor yet. They are both done. I will refer you to my previous remarks about what causes magnetic field, by the way. What causes induced voltage? What did we just do? We just say about the causes for induced voltage. I will also remind you that the equation for induced voltage, here is Faraday's law. Two people have got it. Is it? Is the area changing? Is the field changing? I'm just gonna stand here. This way. What's this symbol mean? Today, gas is $5 a gallon. Tomorrow, by some miracle, this is a lie, gas is $5 a gallon. What is the rate of change of gas price? $0 per day. Is Earth's magnetic field changing? Is the area changing? Is the angle changing? 0 volts, my friends. There is no induced voltage just because there's a flux and a time. There's a delta phi over delta t. Okay, now I'm going to move this at, what is this, 2 meters per second? I'm moving this coil of wire. The coil is moving. Does that movement cause the field inside to change? You decide. You tell me. Is there change in flux now? Google question D. I'm moving the wire. Is the flux changing? Is there induced voltage? You vote. No talking to neighbor, just vote. The vast majority of the first 20 respondents said no, and they're correct. The field of the Earth is really freaking constant. The Earth, as you may have noticed, is large. So as I move along, the magnetic field is not changing. I'm moving this loop of wire. B is the same, A is the same, the angle is the same, no flux, change in flux, no induced voltage. Question. There is flux.
Like the flux of the T.
Then there would be a voltage inducing a current in the line. Then electricity would flow here. Assuming I've got a complete loop. I'm not sure what's that. Okay, now tell me this. I squish the loop. I squeeze the loop. I decrease the area of the loop. Is there a voltage now? Google question. Does electricity flow through this wire? Because of magnetism, based on the laws that we're learning, when I crush it in the presence of the Earth's field. Oh, correct answers. One more time, Google question E. Take a loop of wire in the Earth's magnetic field, perpendicular to the field, smush it, change the area. Is voltage induced? Okay, the correct answer is yes. Is Earth's field changing? Is the area of the loop changing? Yes. So is phi changing? Yes. If phi is changing, then you got a voltage induced. Let's instead of just giving you letters yes, no, true, false statements, let me give you some numbers, because calculating slopes is a skill that has fallen off this semester. First, Harsh, question.
Question about the speed is equals to LV.
Yes.
When you said that the speed is changing.
I kept speed constant.
Okay.
If you speed up, if you step on the gas in a car carrying a load of bar through Earth's magnetic field, but perpendicular to Earth's magnetic field, then absolutely positively induced voltage. We're not going to do that. Beyond the scope of thought.
We're gonna sticking in the speed was changing.
Area was changing in this example. Okay, let me give you an equation and have you practice with this. I'm going to give you a 3 meter by 2 meter loop of wire, big wire. I will hold this up in the magnetic field of the CBAF large acceptance spectrometer, which is a really fancy device that I did my PhD with. And it has a freaking honking magnetic field of 10 Teslas. That's really big. I mean, compared to Earth's magnetic field, micro Teslas compared to 10 Teslas. I am going to ask you, first, let's just calculate the flux. Question first. We'll do that. Let's do that. Let's do that. We'll calculate that. First, just calculate the flux for me. Google question F, what's the flux? As far as, is this a trick question? Someone asked before, everything's a trick until it clicks and then nothing's a trick. Nothing that I do is ever intentionally to screw with you. Wow. Question. Yeah. Thank you. I should be scientific. Calculate for me phi. Phi, Miss America. Anyway. And by the way, if I multiply a field by an area, what must the units be? Teslas times square meters gives you Tesla meter squared. Not Teslas. Flux is not Teslas. Okay, the correct answer is 60. The area is 2 times 3 is 6. The field is 10. 6 times 10 is 60. Now I'm going to give you a formula for magnetic field. A changing magnetic field, and I ask you to calculate the flux at a particular time and its rate of change. I will tell you this magnetic field is a function of time. We're going to start with 5 Teslas. And then every second we're going to subtract off 2 Teslas. Let me make the number bigger. Start with 10 Teslas and we're going to ramp down the field. Every second we decrease it. I'm going to ask you a couple of questions to think about this, to reason through this. What is phi at time 0? What is phi at time 5? What is the change? No. I'm just going to say the induced voltage at time 5 seconds. I want you to assume that we change the field steadily. At time 0 seconds, at time 5 seconds, and then find the voltage at after 5 seconds. Well, of course you're changing the field steadily. I gave you a linear equation for the field. That is a steady change by definition. Correct first person to reply. Oh, this is stupid terminology. I wrote capital T, which is the unit for Tesla. The function is 10, and every second we subtract 2 Tesla. Function is 10 minus 2t, t being time, Tesla. I'm going to write out the word Teslas. There. Stupid Roman alphabet only having 26 letters. And eventually they started using Hebrew letters for some things in advanced mathematics, and at least one guy in advanced programming made his own symbol set. You would have to type with a special keyboard back in the day. It's all about symbols. Hey, time's up. 60,012. Fewer people than I thought put 0 volts at the end. Only a couple of people. I am muy pleased. Let's talk about that in a second. Okay, so how do we do this? We have a formula for magnetic field. I can plug in time equals 0, and I get 2 times 0 is 0. 10 minus 0 is 10. 10 Teslas at time 0 times 6 meters squared. 60 Tesla meters squared, or 60 Weber equivalent. If I plug in after 5 seconds, I get 10 minus 10 is 0. 0 field times area is 0 Tesla meters squared. Now, the check to see if you're reasoning correctly here, where I expected more people to fall on their face with here, is that voltage is not phi divided by t. It is change in phi divided by change in t. How has phi changed over these 5 seconds? By 60 Tesla meters squared. Change in phi equals 60 Tesla meters per squared. How has time changed? 5 seconds, 12 volts. Again, slope ain't value. Slope is the change in one quantity by change in the other. Please. Sure. But the thing is, what's the sign of the voltage? We haven't answered that yet. Plus or minus, who cares yet? You could say negative. I wouldn't take away points for saying negative. But I am going to say the positive versus negative, which way the current flows in the coil, that's big. That's what we're doing. Just about to do now. Questions? Do you feel okay with this? You feel better about this at any rate? Great. Let me give you another puzzle piece. We've got a bit about flux. Now let me give you a bit about how currents make fields. We're switching gears here for a second. We've never done this before. Previously, I've told you this charge feels a field. This loop of wire is in a field, but I haven't told you how fields are made. Sometimes I will give you problems where I just say the field is blank. But now I want you to learn 2 situations where field is created and which way it goes. I have cut out this year, I have cut out how to calculate numerically the amount of field. If you're curious about that, stay after class. We're just talking about directions of fields when I give you a current. For our purposes, I'm going to give you 2 kinds of currents. I'm going to give you straight currents, and I'm going to give you circulating currents. I'm going to give you currents that go in a circle. Now, circulating currents can actually be multiple shapes. In the lab, you will have not just one loop of wire, but a whole spring shape of the loops of wire curling around out of the plane. That actually makes a very nice magnetic field. It ends up being constant everywhere inside the loops. We don't need to care about that. We're not looking at the magnitude of the field, just its direction inside. So if you look end on, if you look at the coil at the spring from the end, it still looks like a circle. Or for that matter, you could have just, scramble wound, just like a whole bunch of turns in one place. That still counts as a circle, even if you've got multiple loops at the same location. Okay. So when I say circular loop, that could be an extended spring shape, a helix, a solenoid, we call them, or it can be a plain circle. Okay, so regardless, I'm going to make current flow in a circle, or I'm going to make current flow along a line. Here's how to find the direction of current with each. I'm actually going to give you an option. We can do a 3-step process with 1 rule, or I can give you additional right-hand rule version. We got some people who want 3 steps, some people who want different right-hand rules. Well, let's do a show of hands. Who wants multiple steps with one rule? Who wants multiple rules, each with one step? Huh? Yeah, there'll be multiple right-hand rules, but each of them is only a single step. Okay, I'm seeing a fair number of both. I'll do both. We'll start with the single right-hand rule. First, I guess we should revisit that right-hand rule because we use it a lot. How do you do right-hand rule? It's not just velocity, cross field is force. I want you to know that there's a first, a second, and a third. The first cross, the second becomes the third. Whatever I list first is your first finger. Whatever I list second is your palm. Your thumb shows the result of that multiplication, that direction multiplication. Here is the formula. If you want to find the field somewhere, you look at the current somewhere, and you can calculate the field that that current makes. That is to say, apply the right-hand rule to a piece of current, first vector. The field point, I'll define this in half a second, second vector, that will give you the direction of the field at that location. Example. Oh, and I have to define field point. Field point is the point where you're looking at the field. Muy importante, the field point is the direction from the current to where you care about the field. For instance, let's find the field point. Let's find the current. Let's find the magnetic field here because of that current. First finger. Which is the first finger? Equation I just wrote down. Current. Which way is the current going in this wire? Right. So which finger do you point right? My first finger. Numero uno. In American, I think anyway. First finger goes right. Which is the second finger, by the way? Second finger. Second direction is your palm. Okay. Which direction is the field point from the perspective of the current? I am the current. Which way do I have to point my palm to get to the field point? I am the current. Imagine being the current. You are the current. The current is you. Which way do I have to go to get to that point? If you are this current, which way do you have to point to get to there? Okay, Google form. I'm hearing like 15 different responses. Google form J. If you are this piece of current, you are flowing right. That actually doesn't matter for the second vector. If you are flowing here, which direction do you have to look if you're looking at that point? If you're looking at, I want to find the field below me. Oh, good, good, okay. I heard like 15 things, but the first dozen are correct. Okay, I am going to be this current. I'm going to look at the field point. Which way am I looking? Down. So the correct answer is your palm points down. The field at this location is into the page. Let's find the field. Whoa, 1 point, not 2. Oh, come on. Zoom, baby, zoom. Stupid freaking. Yeah. Let's find the field above the wire. Which direction is the current point? Still right. Which direction does that current have to look at in order to see where I want the field? Which direction is the field point? Out of the page. Magnetic field above a rightward carrying current is out. A magnetic field below a rightward field is into the page. Hey, What if instead of carrying left to right, I carried in out of the page? What if I am looking end on the wire? Here's a wire carrying current into the page. A long straight wire, not even slightly bicurious. Okay, I'm done with that. A wire is going into the page. Let's find the field. I don't know, right there. Find the field, magnetic field, at a point to the down left of this wire. What does your first finger mean? Direction of the current. Which finger is that? That's this finger. Everyone point in the direction of the current. Schling. Now, imagine being that piece of current. Which direction do you have to look in order to see that field point? I have to look down and left in order to see this field point. This is the direction of the field. Up, left. Magnetic field at this point is up and left. Note, I'm not saying that the field is at an up left point. I'm saying that the field at the field point points up and left because that's the way my thumb was pointing. Above. Tell me the field above. Tell me the field here. First finger in, palm and or middle finger up, thumb right. Okay, Google form. Okay, let's see how everyone is doing. Find the field to the right of an in current. We're almost done with the concepts, by the way. We're really close. Once you guys can do this with the two geometries, the last step is, shouldn't say simple. We're almost done with the second to last chapter of the day. Oh, my sweet baby Jesus, correct. So, first finger is the current point. Second finger is face the field direction, face the field point. If I want to know the field there, I face my palm and or middle finger to the right field, the current is down. You can keep doing this. In fact, if you're not great at right-hand rule, I encourage you, make up an example and do this. At every case, right-hand rule loves right angles, at every case you'll find that the field direction is perpendicular to a radius line. I mean, the field points are always along radius lines. Oh my God, we got a circle. Okay, who wants the alternate version where you have two different right-hand rules, but it's a single step? Yeah, still do that, people? If your thumb is straight, if your current is straight, your field is curvy. If your field is straight, your current is curvy is the thing you have to remember. So I'm giving you two current geometries. I'm giving you a current is straight and giving you a current is curvy. In this case, the current is straight. Here, you don't have three fingers. You have a finger and a sense, a direction, an orientation, a circulation. My right hand, so use your right hand. My thumb is the straight one. Whatever the straight one is my thumb. In this case, the current is straight, so I put my thumb straight. Now, which direction do you notice the fingers of your right hand rotate around? Which direction have I just rotated the fingers? If I'm pointing curved fingers and go in the direction that the fingers naturally curl, which direction have I gone? Clockwise, not rightward, clockwise in the circle. You form circles of field around straight wires and straight field inside circles of field. Straight field inside circles of current. So you have to be able to look at how your fingers curve around your thumb's axis. Are you okay with that? This is frankly faster as soon as you can see the direction of curling. This is from your perspective. What is this? Clockwise or counterclockwise? Clockwise. From your perspective, my fingers are curling clockwise. How about, let me this, at a point above my rightward finger, I'm thumbing right, and current flows right. Which direction, in, out, up, down, left, right, is the field? My fingers are circulating like this, right? What direction is this when my fingers are above my thumb? From my perspective, into the plane. From all y'all's perspective, that way. Shunk. When my fingers are above my thumb, they're pointing out of the whiteboard towards you.
From my perspective, when it goes inside,
When it's above,
we have to take care that what is above.
now when you're talking about when my fingers reach below, that points down here, the field would be pointing in. Pick whichever one you like, use whichever one you like. That's for a straight wire. Now we're going to do it if you got a circulating wire. If you've got, instead of a straight current, you've got a loopy current. I will tell you, I will just give you the hint that the field is strong. Where we are always going to care about the field is in the middle region. And the field always goes perpendicular to the plane of the loop. Second way first. Curl your fingers, hold up your hands so that your fingers are curving counterclockwise. Right? From your perspective, oh, not from your perspective, from any perspective, my fingers are curving in the same direction as that circulation. Which direction is the field inside? Out of the page. The field comes out if your fingers are curling counterclockwise. And that's not just in the dead center, by the way. There's field here, there's field here, there's field here. That's the second way first. Here's the first way first. Consider a little bit of current here. Which way would that current go? I'm going to be this current down here. First finger, current direction. Second finger, let's talk about the field at this location. Face the current. Okay, first finger is going in the direction of this piece of current. Second finger or palm is facing where I want to know the field. Where's my thumb pointing? Out. Out of page. Oh my God, just as like I told you a second ago. It doesn't matter where you pick. Let's find up here. If this is current circulating counterclockwise, then this current is up. This bit of current over here. Which way does your first finger point? First finger is the current, finger points up. Second finger or palm. If this is the current, which direction does it make the field at the middle of the loop, let's say? Your palm goes towards, facing, from this guy's perspective, facing the field point. Which direction was your thumb then? So the field here comes out of page. You don't like that. You did it right though. If you do you like this way? You don't like this way? Okay. Some people find it one way, some people find it another. You now have everything you need in order to answer Lenz's law questions, to understand Lenz's law, to do Lenz's law. Lenz's law has 4 steps. Jean-Luc Picard told us there are 4 steps. Step uno, write this down. Unless you were here yesterday class and stuck around. Find original flux direction. Find the direction that the original starting primary main flux is going. Step 2, that can be bigger or smaller. If it's not changing, no change in flux, there is no voltage. So is it increasing flux or decreasing flux in the direction you just found? Step trace is which direction opposes that change? Very important. Which opposes the change, not the flux, but the change in flux. Which direction opposes the change? You just identified how the first flux is changing. Now I want you to identify the reaction that opposes the change. Step 4, work backwards from the new right-hand rules that we just discovered. Well, that I told you. Work backwards to find the current that would make that reaction flux. Here is a loop of wire. Here is a second loop of wire. I'm going to pass current clockwise or counterclockwise, doesn't matter. I'm going to pass current clockwise through the main loop of wire, the first loop of wire. I'm going to ask you if I am increasing this current. This is current 1. There are two currents, current in blue and the current in red. If I increase the current in 1, let's do step by step to find out which direction current in 2 goes. Step uno, Google question L so I could check on everyone. Step 1, what was step 1? Find the way the original flux goes. Which direction is the flux inside this current? Inside this loop. Got a counterclockwise current. Which way does that flux it? First person is correct. The field is straight now. Clockwise is not a possible answer. And don't tell me find original flux. I want a direction. My question again is, which direction is the flux because of this wire? Because of this initial loop? The flux is either in or out. The flux is not clockwise or counterclockwise. The field is straight if the current is loopy. Yes, I recognize this is frustrating for some of you. Some of you because it's too easy, some of you because it's too hard. Some of you because you got it 5 hours ago, some of it because it's going to take some more practice before you get it. I should say it that way. Be patient. Both groups. At least I presume that's why some people are typing in all caps. And is in fact, the correct answer. How do we know this? Well, second way first, if your fingers rotate clockwise, which direction is your thumb pointing? Shrink into the page. Second way of finding it, let's imagine being this bottom piece of current. What's my first finger do? Bonk. What's my second finger and or thumb do? Bonk. If I'm looking for the direction of the field at the location of the red loop, bonk into the page. Field, initial flux goes in. Now, step 2. What's step 2? Yeah. Sure. curl your fingers, hold up your right hand and curl your fingers so that they are going so they're going clockwise in this plane. Now curl the fingers. If your fingers are rotating clockwise around the axis of your thumb, I'm always thinking of relative to my thumb. I don't think I said that out loud. Imagine circulating around your thumb. Well, how do I have to hold my hand so that they're making a circle around the axis of my thumb that mirrors the current? This way. You know, which way is your thumb going? Shrink. Field is in. Step 2. What's step 2? Is this flux increasing or decreasing? Is it getting bigger or smaller? Which, just say it out loud. Increasing. You make a stronger current, it makes a stronger field. I mean, kind of duh, right? Step trace, how do I oppose an increase in infield? Put this at the Google form. Google question M. I've got inward field, which is getting bigger. Do I want an infield or an outfield to oppose that? Almost everyone. Good. Don't tell me what the original is doing. Tell me how to oppose his change. If I am getting more and more in, the correct answer, to oppose the increase in infield, the reaction current wants to make outfield. So step 3, the correct answer is out. Again, if the inward pointing field is getting stronger because current is increasing, stronger inward pointing field, I want to oppose the increase by pointing out. The reaction field points out. Okay, so now you know the reaction field points out. How do I have to circulate current through red wire in order to get an outward pointing field? Hold your hand up to show me. How do I circulate wire, counterclockwise or clockwise, in the red wire to get the field to point out? Use your right hand.
Yesterday, did you say, the direction stays the same, but the intensity?
Oh, it does.
opposite?
It does.
So,
The intensity does.
yeah, but the direction stays the same.
Yes. Unless you change how this is increasing or decreasing.
So what would be the opposition of, maybe?
To oppose an increasing in, out. I'm not sure I'm answering the question you're asking.
Yeah, because yesterday you said that the opposite would be left, if it is left with high intensity, it will be left with low intensity.
If it's left and increasing, then you want to point right, not left. And it's not high-low intensity, it's increasing or decreasing intensity. Are you getting stronger left? Getting weaker left? Yes, that's what I mean by the direction of flux. Yeah. Okay, so the correct answer, la respuesta correcta, is I have to circulate my hands counterclockwise around this in order to make an outward pointing reaction field. So the reaction current points in the opposite direction. Ah, for God's sake. The reaction current points in the opposite direction as the original current. Does the reaction current always point in the opposite direction? Niet, nein, nichts, no. What if the field is getting weaker? If I drop the current, if I decrease the original current, what is the change now in the original field? I am weakening my infield, right? How do I oppose a weakening infield? Everyone, Google form, wake up. Google question N. I have an inward field which is getting weaker. What do I have to do to oppose that change? What direction do you want your reaction field to be to oppose the weakening infield? Correct answers are in or out. Field is pointing in or out in this example.
So it's weekend.
Yeah, I'm saying now the current is decreasing instead of increasing. The original current is decreasing. So I'm getting less and less inward pointing field. Okay, let's see what everyone thinks. Not getting very many votes here, but everyone who's answering is saying in. Not everyone. The majority is saying in, which is correct. If I've got less and less in, I oppose that decrease. I oppose the loss of in. I make up for that change by pointing in as well. Now think to yourself, what direction is the current here? What direction does this current have to go in order to make an inward pointing field? How do I make an in field? Must be the same direction as the original current. Feel okay with this? Oui, da, rien, see? Did it, da, did it? Okay. We are just about done, which is good because we're just about out of time. I want to give another example where we've got not a where we've got a constant current that changed something about the area. I'm going to drag a loop of wire away from a constant current. So here is my constant current. Here is I1. I'm going to make a loop of wire, and I'm going to drag this loop away. You do not have the mathematics to calculate the magnitude, but I want you to calculate the direction of current in the loop as the field in it gets weaker and weaker. It is being pulled away from the constant current. Ready, set, go? If you could do this correct, I'll let you go. Google question O. Yeah, I take a loop of wire above a rightward pointing straight line of current. I drag this loop of wire up, away from the current, weakening field. Which direction does the current have to point in the loop, clockwise or counterclockwise, in order to make up for the missing flux? 4 steps, work them out. If you could do this, Google question O, or oh my God. The logical choices here are clockwise or counterclockwise. I'm not asking flux. I'm not asking field. I'm asking for which direction the current would flow in the second. Hint, it's clockwise or counterclockwise. Out is not a possible direction that the current can flow. Right is not a possible direction the current can flow in the loop. Okay, here are the steps. I want to give you the answer to the last homework quiz, the last quiz question. So work through this and I'll give that and I'll let you go. The correct answer is counterclockwise. Let's see why. Which direction is the original flux? Shrink out. You get that the original flux is out. You see that. The original flux due to the red wire in the plane of the blue wire is out of the page. Now I see a lot of either tired or confused faces, and I can't tell which. Okay, so the original wire makes an out of field, out of page flux. Now I'm dragging the loop away. Does that mean that the flux is increasing or decreasing? Getting further away from your magnet. Decreasing flux. I'm losing out field. What do I have to do to make up for that? If I'm losing outfield, I need an outfield to replace it. So what direction current makes an outward pointing field? I got a loop of wire. What direction is my current? Counterclockwise. Current must go counterclockwise in this. Wait, no, you don't like it? Well, I'm pushing things so we can go deeper into this next week. Go ahead. Yes? Precisely. Okay, I will now give you how to do the last homework quiz question. If I can find it. The trick here is thou shalt look muy carefully at the diagram. You have to look very carefully at the diagram. If you do not look closely at the diagram, you will die. It sucks. I'm sorry. Perspective drawings are hell. But what can we do? The world is three-dimensional. Here is a loop of wire wrapped around an iron core that vastly increases the magnetism, by the way. This is how you would actually do it if you want to measure the stuff. Looky carefully at how the battery and how the wire are connected. The battery positive side is on the left. The coil wraps up behind the magnet, out, down in front of the magnet, then back in, yes? Okay, curl thine fingers, show me the direction of the field when I turn the battery on. When I apply voltage from the battery, which direction is the current going to make a field inside this core? I start with the battery, the switch open, no electricity flowing. Now the battery starts flowing electricity out the positive end. Which direction is the current circulating? Current circulates from my perspective, the current is circulating up the back, out the top, down the right, in the front, in the bottom. That's this sense. That's clockwise from my perspective. The field from the primary coil is to the right. I started with no current. I then turned the current on. Have I increased or decreased my right? I've increased the right. What does the secondary, the other piece of wire want to do? Does it want to help that increase or oppose that increase? If you're increasing right field, you react to an increasing right field by making a left field. Which direction do you have to circulate in a loop to make left field? Go on, show me with your hands. Hold your hands so that you can show me. If this is loop, I'm looking at the circle, you're looking at an end on, your hand will be either this way or this way. Show me your hand so that you're making a leftward field, opposing that, circulating the current clockwise or counterclockwise from my perspective. Make a left field, it's gotta be, from my perspective, counterclockwise, up in front, back on top, down and behind from your perspective. Looking at this end on, the correct answer is counterclockwise. What would happen if I never turn on the switch? No reaction current. What happens if I leave the switch on for like forever? No reaction current. If you're not changing crap, you never get an induced voltage. We're out of time. Remember what I said at the beginning of class. I will see you next week.